Okay, so hello everyone, and I welcome you all to this week 4 discussion session. In this session, I solved some problems related to your assignments. This is week 4 discussion session, and here I will discuss some problems related to week 4 assignments, which basically consist of some problems related to Josephson Johnson's and squids. So that being said, let's start with the discussion session. Let me share my screen. Okay, so I hope you all can see this PowerPoint presentation slide. So I'll start with the first problem that's related to the IP characteristics of a normal metal and superconductor interface. So basically we'll study how if we apply a voltage across the normal metal and superconductor interface, how the current changes with the value of the voltage. Okay. So um, so let's first try to draw a normal superconductor interface. Okay. So let's say this is a normal metal. uh, we have one superconductor in the right hand side. So this is superconductor and this is non-conductor. And we have to apply a voltage across this junction. This is closed. Okay. And at the same time, we also want to measure the current. Okay. So the voltage is applied through this, and we also want to measure the current. So we're basically trying to do a two-pole measurement in the normal metal superconductor interface. Now, what happens when we do this? So we know that in the case of a superconductor, so a band gap, if we draw the density of state distribution with energy, so let's say this is density of state, and sorry, so let's say this is energy E, density of state axis. So we know that in the case of a superconductor, in the case of a superconductor, so band gap generally appears in the Fermi surface. Okay, so let's say this is Fermi energy EA. So we know that in this region around the Fermi energy, there is no density of states. Okay, so this region is basically vacant, and the width of this region is called 2 delta. Okay, where delta is the gap of the superconductor. Okay. This gap appears in the gap equation. So, and this state electron get emitted there, and electron can exist here also. So can excited go and excited to this region. But in this region around the Fermi surface, in the 2 delta energy region, there can be no empty density of state for electrons. Okay, so electron cannot exist in this region. Now, in the case of a normal metal, if this is the Fermi energy of the normal metal, okay, so electron can jump out of here. So this is not like it's not like so. In this, let's say this is the normal metal, and this is the Fermi energy for normal metal. So electron can exist here, uh, but also electron can excite and go to this region. So there is not like this case. Okay, so it's not like there is no electron can exist in this region. There is no gap in the Fermi energy in the case of a normal metal. So electron can readily excited here. Okay, now when we make a junction out of this normal metal and this superconductor. Okay, so once again I am repeating. So we're starting with the week 4 interactive session, and We are trying to discuss the IV characteristic of a normal metal and superconductor interface in the first question. Okay. So let's say that we have a normal metal in the left hand side, and the right hand side we have a superconductor, and we make a junction out of this. So we want to see how the IV characteristic appears for the case of this junction. Okay. Now we have made the circuit like this, where we have applied a external voltage here, variable voltage, and we also same time measuring the current through this circuit. Okay. So this is like a two-probe measurement. Now to actually derive how this IV characteristic will look like in this junction, we have to first see what is the density of state that appears in the case of a normal region, normal metal, and the superconductor. Okay. Now in the case of a superconductor, we know that if this is the Fermi energy and this is the energy axis and this is the density of state, then in the case of a superconductor, a gap appears at the Fermi energy. So there is basically a 2 delta energy region around this Fermi energy EF, where there cannot any free electrons or single electron that can exist. Okay. So all the electrons in this region, they make Cooper pairs. So no single electron state exists in this region. Okay. That is why this is called a gap, superconductor gap in the case of a superconductor. And this gap appears in the gap equation also. But anyway, so the electron cannot get excited and jump into this region. If they have to get excited and jump, they only have this region to get excited. Okay. So these energy regions are single electron state, and this can be available for the electrons to get excited and jump into. Okay. But in the case of a normal metal, we know that in the Fermi energy, no gap appears in the Fermi energy level. Okay. So around this Fermi energy level, all the electrons are single electron state. Okay. No gap appears in the case of a normal metal. So electron can readily jump into this region when they get excited. Now when we apply the voltage around this junction, okay, so this is the normal metal and superconductor junction. When we apply the voltage around this region, the electrons in this normal metal, they get some energy and they try to get excited. And but in that we can see that if they get excited, they have no way to jump, because unless and until they have energy greater than delta. Because if they want to get excited and go to the superconducting state, they only have to jump here. Okay. And this value is delta. Okay. So they have to get excited by this much energy to actually penetrate the surface and go to the superconductor. Okay. Now, so the only condition for the current to flow in this circuit is that the voltage that the electron gets, so the voltage that we apply from outside, this voltage should cause the excitation in the electrons energy by an amount of delta. Okay. Otherwise, there will not be any flow of electrons, and there will not be any current flowing in the circuit. Okay. So the condition is the voltage V in the circuit should be such that they creates excitation by an amount delta. Okay. So only when this amount of excitation the electrons get, then only can these Cooper pairs in this region, they can get excited and jump into this region. Okay. So now if we know that the electrons if an electron resides in a voltage V, so if we apply a voltage on the top of an electron, its energy is EV, electron volt. Okay. Now in the case of a Cooper pair, we know that a Cooper pair has total charge 2E. Okay. So if we apply a voltage V on the top of a Cooper pair, the total energy of this Cooper pair will be 2 electron volt. Okay. 2 EV. And as per our condition, to get a flow of current, this 2 EV should be greater than or equal to delta. Okay. So the change in energy must have to be greater than or equal to this gap, so that the electron can jump into this region. And from here we get a condition that V should be greater than or equal to delta by 2E. So our final condition is like this: V is greater than delta by 2E, current exists. Okay, current is not equal to 0. But when V is less than delta by 2E, current is equal to 0. Current in the circuit is equal to 0. Now from here we can see how the IV characteristics would be for this case. So what will be the case? So up to some amount, that is delta by 2E, whenever V is less than this delta by 2E, there will be no current. So here the current will be 0. And as soon as we go above this voltage delta by 2E, we get some finite current. Okay. So this will be the IV characteristic of the junction. Okay, so we are done with the first case. Now let's say we want to make a Josephson junction. As you may have known by this time, so we have, if you have seen the with 4 lectures, so you will see that so in the case of a Josephson junction, this there is not only the normal metal and superconductor junction, it will be like this. So this normal metal will be, this is the normal metal region. In the case of a Josephson junction, this has to be sandwiched between two superconductors. So there should be one superconductor in the left and one superconductor in the right to this. Okay, and this normal metal region, this is very thin in width. Okay, this normal metal is very thin in the order of nanometer. Okay, so this should be in the order of nanometer, or in the order of penetration depth of this, in the order of coherence length of this superconductor pairs. Okay. So otherwise, if this region is in the width of this region is greater than the penetration depth, or the sorry, not the penetration depth, uh, but the coherence length of these Cooper pairs, the Cooper pair currents cannot penetrate through this region. Okay. So the width of this region must have to be lesser than the coherence length of Cooper pairs of the superconductors in this region and this region. And the coherence length of the Cooper pairs is generally in the nanometer range, and that is why the width of this region, this normal meter region, that is very thin, and that is in the order of nanometer. Okay, that being said, now what happens in this case of the junction. Okay, so this is called the Josephson junction. So now let's say we want to try to do the same measurement, basically the two-prong measurement on this Josephson junction. Okay, so we want to apply a voltage. And the same, we want to apply a voltage, and also want to measure a voltage around this, and we want to see in the, as a function of this voltage, how much voltage that appears across this region. Okay, so this is also like a two-prong measurement. So you want to connect a voltmeter here, and we want to see how much voltage appears across this region as we apply some voltage from here. So this is the complete circuit of the Josephson junction. This is all connected. So now I want to see how the IV characteristic appears. Question 2 is related to IV characteristics of a Josephson junction. Okay. So in contrast to the normal superconductor interface, in contrast to this case, in the case of a superconductor Josephson junction, we will see that without applying a voltage, if the voltage axis, we already get some current flowing in the circuit. Okay, we don't have to apply an initial voltage. We already get some current that is called the critical current that is flown from this that is flowing in the circuit. We will observe. Okay, and why this happens? Because as you already said that the normal metal this normal metal interface is very thin. This is less than the coherence length of the Cooper pairs. So the Cooper pair wave functions they can penetrate through this region and go to the other region, other superconducting region. So the Cooper pairs from this region can go to this region, and also in the inverse way, this Cooper pairs from this region can penetrate to this region. Okay. So due to this influence, some without applying, even we don't apply the external voltage, we also get some current. Okay, in the circuit. So the circuit, the current in the circuit I is not zero, even if V is zero. So this is in contrast, as you can see in the last time we got this condition. So to get a current that is non-zero, we must have to apply external voltage that is greater than this amount. But in this case, the voltage is not required, and we already get a current that is equal to IC. Okay. So and on the top of this, if we try to apply a voltage from here, we will see that a current flowing through the surface evolves like this. Okay. So this is the IP characteristic of a Josephson junction. Now let's try to understand how how the characteristic that appears in the case of Josephson junction that appears here. Okay. So let's draw the junction. This is region L, superconducting region L, superconducting region R, and this is the normal metal region. Okay. Now let's say the wave function of the Cooper pairs that is appearing here, that is given by this. As you know from the last interactive session or the week 3 lectures, the electrons in the superconducting pairs in the superconducting metal or a superconducting sample is phase locked, and that can be expressed by this macroscopic equation, where the phase of all electrons is given by this delta 1, and the amplitude of the wave function is given by psi naught. Okay, and the density of the superconducting Cooper pairs is given by psi star psi, that is equal to mod psi square. Now say let's assume the phase in the left superconducting region and the phase in the right superconducting region, they are not same. Okay, they are independent of each other, and the phase can be written as delta 1 in left superconducting region and delta 2 in right superconducting region. Now what happens is that the wave function, okay, so the wave function, let's say the amplitude of the wave function is psi naught here. Okay, that is constant inside the superconductor. But as soon as it approaches this normal metal region, it starts to decay because it's not a superconducting region anymore. So the density of Cooper pairs gets decreased in this region. But still, some part of this wave function that turns through this normal metal region and enters to the right superconducting region. Okay, so there is some finite amount of density of Cooper pairs that is coming from the left superconducting region that exists in the right superconductors, or that enters to the right superconductor. Similarly, in the case of a right superconductor, we see that in the entire superconducting region, we have a constant density of Cooper pairs inside the superconductor. But as soon as it approaches this normal metal, it starts to get decrease, but still it penetrates to this normal metal, and some amount of the density of Cooper pairs that enters in the left superconductor. Okay, so we know that so from here we can see that some amount of electrons or density of state of Cooper pairs that exists or that can penetrate this normal metal, and that can flow from one region to another. And this flow of Cooper pairs from one superconducting region to another superconducting region, this gives us the current in the absence of an electron, in the absence of an external field, okay, or external voltage. So that is how we get this property of the characteristics in the case of the Cooper pair, okay, in the case of the Josephson groups. So this is IC, and without applying a voltage, we get a certain amount of current flowing through this circuit. If you make a throughput measurement of this. Now let's try to understand the. Okay, now you may have known by now that the Josephson relations. Josephson relations. There are two well-known Josephson relations, and that appears in the case of when we study in the Josephson junction, and they are given by these two. Okay, so the first Josephson relation is given by that the current that is flowing through the circuit is IC times sine of delta, where delta is equal to delta 1 minus delta 2. That means the phase difference of electrons in this region minus the phase difference of the phase of electrons in this region. Okay, so this is basically the phase difference. In left and right superconducting regions. So this is the first Josephson relation, and the second Josephson relation is given by this. The time evolution of this phase difference is governed by the voltage that is applied across the interface for the Josephson junction, and this is related by this equation. Okay, this is our second Josephson relation. So in question number 3, we'll try to derive first and second Josephson relations. Okay, so let's try to derive our first and second Josephson relation. So let's draw the Josephson junction again here. This is normal metal, superconducting region 1, superconducting region 2. This is the left and right. So as we know, in the case of we have already used this many times. So the density of the wave function of the electrons in the case of a superconductor is given macroscopically by this equation, where the density is given by mod sine naught square. So basically sine naught is equal to 2 root over 1 naught. Okay. Now the dynamics of the wave function. Dynamic of the wave function of the electron of the Cooper pairs is given by the Schrodinger equation that we already know. Now let's assume that the wave function of superconducting region 1 or the left superconducting region, the right superconducting region, yeah, that is given by this. psi L is equal to rho n to the power half. So this is basically psi, you can write psi naught n into e to the power I phi n. But we can know from here that I naught is equal to what? Rho naught. So we can write this as rho naught L to the power half into e to the power I phi n. Similarly, psi of r is equal to rho r to the power half into e to the power I phi I. Okay. So we have these two equations in our hand, and now we will proceed with this. Okay. Now, if we try to write the superconducting, the Schrodinger's equation for the left and the right region. So ideally, this would be like this. Sorry. Okay. So ideally, this would be like this, but this is not the general case. So in the case of the in this specific case, it's modified by some amount due to some leaking of these super pairs across the junction. Okay. So this will get modified, and here there should be some term here. Okay. So uh, so let's take a break for some time, and I will come back after one. Okay, so let's get back to this equation, and so the modified term would be there due to so some Cooper pair leaks through this normal metal junction, and that's why there should be some modification in this region. Okay, left and right superconducting region. Let's say some Cooper pairs enter to the left region from the right region due to leakage, and the energy of these Cooper pair wave functions is given by k. Okay, some constant k. Now the equation then get modified like this. Okay. Similarly, this is our modified Schrodinger's equation. Now let's say we're applying the voltage V across this junction. Okay, so we are now applying a voltage V across this reception junction. So what will be the energy of these electrons then? Energy of the left electrons will be EV, and the energy in the right electrons will be minus electron. EV. Why this is minus? Because the electrons in this region, they are connected to the positive charge, positive region of this battery. But the electrons in this region, that is connected to the negative end of this battery. So it will get the negative potential, it will get the positive potential. That is why the energy of the left electrons and the energy of the right electrons, they are opposite in sign to each other. Okay. So now let's put this in the Schrodinger's equation. Equation. Now let's just prove the value of this psi L. So the value of the psi L is assumed to be this, the expression of the psi L. Putting this in equation 1. What do we get? We get, first it operates on this rho L. Then it operates on this time. So what do we get here from here? So the I and the outside I, they gets multiplied and gives the minus sign. Okay, so we get this. That is equal to E T into L to the power of to the power I for L. This is our I phi L and plus this region. Okay, so in the case of phi R or to psi R, so we assume this form or this expression of psi R. So we'll put that here. Okay, so now let's divide. Divide by this. Let's divide this whole equation by this term. What do we get? We get this term here minus this total term goes out here. there should be H coming. Okay, so now we have this equation without them. Now we can write this term this e to the power I5 as this. So we break it into the real part and the imaginary part. Putting that in that previous equation, what do we get? We get I by 2 rho L d 2 rho L by dt. Okay, now let's equate the real parts and imaginary parts. Real parts and imaginary parts of the equation. Okay, so this is imaginary part, and in the right hand side, this is our imaginary part. It's I terms. Okay, so I by 2L, so this is imaginary part. I by 2 over d into by dt is equal to, so I can cancel from each side. A by h bar for half sine pi n pi n. Okay, and the imaginary part and the real part is this one and this one and this one. So the real part is so we have now equated the real part and imaginary part here. So and this is basically what this is the phase difference. Of left superconducting region and right superconducting region over phase. So let us denote this by this. Let us denote the phase difference by this term delta. Okay, so then this term gets modified to this. So you can now write this as d into L by dt is equal to 2k by h square. So this 2 goes here into rho L rho L equal to 1 into sine. Now this term is delta sine delta. So this is equal to, okay, so this is equal to this del of rho L by dt is equal to this term, and from here we also this term. So similarly, if we do the same thing for the right hand superconductor, okay, so yes, I think this is clear. So for the we started deriving all these things by substituting this in equation number 1. Okay, so from equation number 1, what do we get by creating the real part we did get d rho L by dt is equal to 2k by h car into sorry, this is sine delta. Okay, so we have just derived this in the last slide, and also in the case of Machaneka, we got this 8d into the phi L by dt. This equation, we take the minus sign in the right hand side. Minus EP by h car minus a by h and we put again the case of the theta in the place of theta minus theta a, we again put the delta sum. So this is what we get from equation number 1. Same thing if we do for equation number 2 in the place of this psi r. If we put the value of expression of psi r like rho r to the power half to the power I phi and use this expression in the equation number 2, you can verify that we will get these two equations. By equating the real part, we will get d of rho r by dt equal to 2k by h car rho r rho a equal to half sine delta and by equating the imaginary part we will get like this. We will get k by h car rho r by rho r. This time rho r is in the denominator. Okay. So this is the equations that we will get from equation number 2. Now what we get? So this is our, let's say, equation number 3. Equation number 4. Now let's just deduct this term from this term, or the first this equation from this equation. So if we subtract this equation, we're subtracting this equation from this equation, so what we will get? So these two terms cancels out. We will get 2dv by h or d of delta by dt equal to 2ev by h, because delta is phi as we have assumed before, and as you may have noticed by now that we have these two reception relation too. So this was our second reception relation. Okay. So the second reception relation was this. So we have now reached to the second reception relation. So this is the proof of our second reception. But we have not yet proved the first reception relation. So let's try to prove that also. Question number 4. First reception relation derivation. Using the same knowledge. Okay, so we have got many equations from this term. Now we will use this equation derive our Josephson relation number 1, our first Josephson relation. So the density of current, we can say that the density of current that is flowing to this flowing through this Josephson junction. So let's say the density of Cooper pairs in this region are NS1 and in this region are NS2. So anyway, the Cooper pairs are flowing through this region. So the density of these Cooper pairs, they will change by time. Okay, and due to this flow of these Cooper pairs, the current density that we are getting, that is given by this equation. So the charge of Cooper pairs times the rate of change of this density of Cooper pairs. Okay, so the density of Cooper pairs is given by rho L. So let's keep the notation same. So this is rho L. Okay. So in the case of the left junction, left superconductor, we can write the density of current as this: the rate of change of the density of state of Cooper pairs times the charge of the Cooper pairs. Okay. Similarly, also in the case of the right superconductor, what do we get? In the case of the right superconductor, we get just the rho L changes to rho L because we are now in the right region. Okay, so this is how the density of current is given in the case of that is passing through this Josephson junction. Okay. Now from this equation, we got did we get this is dl by d rho L by dt or d rho R by dt. They are same basically, and then they are given by this term. So these two things are same. Also, we can get from this equation. So now if we put the value of this d rho R by dt on this equation, we are getting the value of d rho R by dt by this. That is equal to 2k by h cut rho L rho R rho L per half of sine theta, sine delta. Okay. So now we put this value here in the equation and we get this. Now, okay, so simplify it with further 4dk by h cut to 1. Now, in the case of this Josephson junction, the density of Cooper pairs in the left superconducting region, the density of Cooper pairs in the left superconducting region is rho L, and the density of Cooper pairs in the right superconducting region, that is given by rho R. They are almost same. Okay, they don't vary too much. So we can express this rho R and rho L like this, that is equal to some constant rho. Okay, that represents the density of Cooper pairs both in the left zone and the right zone. So if we now put this in this equation, what we will get? Rho. So this rho square to the power half. That gives us rho into sine delta. And the density, okay, now this can also be written as like this: J naught sine delta, where we have assumed that J naught is given by minus 4 k rho by h cut. So what do we get finally? J is equal to J naught by sine delta. So as you can see that we are quite close to the Josephson consideration that is given by R is equal to R sine delta. But we have not quite actually derived this equation yet. So we have to further derive that equation by using this equation. Okay. So to do that, what we will do? We will basically just have to integrate this over the surface of the interface. So if we do the integration on the surface of the interface, so this gives us this value I, and this gives us the critical value. So finally we get the fast reception location. So this is how the fast reception can be derived using the very simplistic form of the wave function of electrons in the case of a superconductor that is given by the microscopic wave function equation psi naught e to the power I. Starting from the very first point and using the Schrodinger's equation and the information that what pairs that leads through this interface, we can derive and reach to this first relation and the second relation. Okay, so this ends our discussion on these reception junctions. In without a magnetic field applied. Okay, now till now we have not applied any magnetic field on the top of this reception junction. So question number 5 will be about reception junction in the presence of magnetic. So this will be our next next aim to or the next lesson to derive how in the presence of a magnetic field the characteristics or the IV characteristic changes in the case of the perception function. So before that, let's take a break for 1 or 2 minutes, and after that I will resume. Okay, so let's resume our discussion session. And in the now we will study how in the presence of a magnetic field the IV characteristics of just junction gets modified. Okay, so for that we will try to draw a junction first. So let's say the superconducting region is the normal metal, and this is the second superconducting region. Superconducting region 1, superconducting region 2, and this is the normal metal. Now what will happen? So what will happen when we apply a magnetic field in this region? Okay, this magnetic field B. So let's say the magnetic field is applied across the plane. Okay, the magnetic field is applied along the perpendicular to the plane of the reception junction. So, okay, so the direction is magnetic field is noted by this distance. And okay, so now we'll start from the Ginzburg-Landau theory, where we had derived in the previous session that the from the second GL equation we can reach to this equation basically that is given by this. So had derived this equation already in the earlier discussion session. Now we start from this equation and try to derive or try to see how the current versus this how these currents in the resistance junction that gets modified in the presence of this magnetic field. Okay. Now this phi naught can be written as this also. The second term on the right hand side. The term on the right hand side can be written as this. Grad of phi dot dl. Why? Because this term denotes the so we had derived this equation in the context of vortice in the superconductor. Okay. And this delta phi, this gives us the change of the electron's wave function's phase when we go one time around this vortices. Okay. So that can be written by this equation. Now we'll make use of this equation and to finally derive how the current equation that gets modified. So now we can choose a path around this normal metal region. So let us choose a path like this. By choosing a path around this normal metal region, and let's say we go around this way. Okay, so a path convention is like this. Now let's say the width of this normal metal region is given by T effective. So the width of this normal metal region is given by T effective, and also the path is a certain amount distance that is given by lambda. Okay. So the penetration depth. Okay, so what can we do is continue. Okay. So the width of this normal metal region that is given by this value P effective, and okay, so let's say our path is drawn in such a way. It is a certain distance lambda away from this normal metal. Okay, so the internal distance between this path and this normal metal region is lambda, so that the magnetic field that is present in the case of normal metal that cannot reach here. Okay. So basically along this path the current density J is 0, and that's why this equation gets modified to this equation. Now also this phi can be written as, this is the flux due to the magnetic field, so this flux can be written as V dot ds. Or this can be in other way around, we can write it as delta of C gradient of phi dot d is equal to 2 by h cut into V dot ds. Now let's give a name of this path, that is A, B, C, D. So over the AB region, AB and CD region, the phase is constant. Okay. So what is the AB region? This region, and this region. So as it's not crossing the magnetic field of the normal metal region, so it's inside a superconductor. we know that in this superconductor the phase change from electron to electron, they are phase locked. So that's why the electron's phase is not changing along this path. The path AV and this path, that's CD, that's also inside the superconductor. So then this term, this C into grad of phi dot dl, this can be modified to this equation. Okay. BC grad of phi dot dl plus dA. So we are only taking the region where this phi is actually present. Okay. So this is given by phi k minus phi 2b, sorry, phi 1c minus phi 2b, and phi 2a minus phi 1b. Why it's like this? This 1 denotes the superconducting region 1 that we are denoted here. Okay, we have not denoted here, so let's denote this by 1, this by region 2. So 1D, this means the D point in superconducting region 1, 2A means the point A in superconducting region 2. And okay, so this clear now. Now we can also write this as this phi 1c minus phi 2b minus phi 1d minus phi 2a. And this gives us the change of this phi. Okay, so let's say this region. So let's say this region along, so let's say we have assumed the axis, this axis as x-axis. Okay, so let's say this point is x, and then this distance is delta x, so this point is x plus delta x. So when we jump from this point to this point, this means the phi have changed by some amount, and that change is denoted by this. When we jump from this point to this point, that phi have changed by some amount, and that is given by this. So we are basically giving the change in phi as a function of where it changes, the position. Okay, so as a function of the position. So we can write this as delta. So this phi c minus 2b, as you can see from here, phi c minus phi 2b minus phi 1c. This means we are noticing the change in this position along x-axis. Okay, so at x plus delta x, we are noticing how much this phi changes as we go from region 2b to region 1c. So that is why we denote this by x plus delta x. Similarly, we can denote this by delta x. So this is up to how well we have derived till now. Now after this, also we do know that the also we know that the total magnetic phase flux total magnetic flux is given by the total magnetic flux through the normal metal region, that's given by this equation, d dot ds dx, because we are only considering, so our normal metal region was like this, superconducting region 1, superconducting region 2, and our path was like this. Okay, so the part of the normal metal region that is inside this path, that is given by this region only. Now we have to find out the area of this region. then only we can find out how much flux is flowing through this region. So this is already I have mentioned is dx, and this is T effective, the width of this normal metal region. So the total area of this region is T effective times dx, and the B is the value of the magnitude of magnetic field. So that's why the total flux is given by this. Now also again from this equation we have derived this. So from here we will put the value of this thing and this thing. So B T effective dx is equal to h cut by 2e, h cut by 2e times delta of x plus dx minus delta of, because we derived this term is given by this, so we have put that in this equation. This is our final conclusion from the derivation. Okay, not the final, but this now till now we have derived it. So now also we can write this thing as d of delta x. So from this equation we get d of delta of x is equal to 2e by h cut into b t effective dx. Now what can we do? Write this as h cut, we can write as h cut is equal to h by 2 pi, we know. So if I write this here, so this will be like 2 pi by h cut, not h cut but h, and this, if we take this 2 from the denominator, it will be like this. So this will give us 2 pi by phi naught to be effective into dx. Where this phi naught is h by 2e, or this is called the flux quantum. Okay. So as you may have already known that this term is called flux quantum. So what was flux quantum? We discussed this in the last lecture. So if we consider some vortices inside a superconductor, the magnetic, and we apply magnetic flux from outside, magnetic field from outside, then the magnetic flux that each vortice can contain is given some number, integer number a times this flux quantum. Okay, so the magnetic flux that can pass through these vortices are not arbitrary; they are quantized, and they can be either. So the value of a is equal to 0, 1, 2, 3, 4, or 0. So the value of this flux quantum, the value of the magnetic flux that can pass through each vortices can only be either phi naught, 2 phi naught, 3 phi naught, etc. Okay, so they are not quantized, and that is why they are called the flux quantum. Okay. So so this is how much we have derived till now. So now we will proceed with this equation in our hand. Okay, so our final equation is like this. Psi naught d t effective into dx. So now we have this equation in our hand, and now we will proceed with this equation to finally reach the value of to finally see how the current through the suspension junction that gets modified in the presence of a magnetic field. Okay. So equation was like this. Now let's integrate this. So by doing the integration over h, what do we get? Plus some constant that we can represent by delta naught. Okay, so this is the final form of this spatial evolution of this phase factor delta, okay, or the phase difference. So this phase difference, so what was our x? So our Josephson junctions was like this. So this is superconducting region 1, this is superconducting region 2, this is the normal metal, and our x-axis like this. So this delta x, that represents how, so this delta, first of all, this represents the phase difference between of electrons between this region and this region. So delta x represents how this phase difference that evolves if we go along the x-axis, so in this direction, okay. So if we go along this direction, how much this phase difference that evolves with the spatial position. Now if we put it in our previous equation of current density of the Josephson junction that was given by this equation. Now if we put in the place of delta, if we put the value of delta x, then we will get g of x is equal to gc of 0 to sine of 2 pi p t effective x of phi naught plus delta naught. Okay. And that can be all written as also like this, sine 2 pi x by lambda j. The lambda j is a length scale that appears in the when we try to solve things in the Josephson junction. So the lambda j is a characteristic length scale in the case of a Josephson junction, and that is given by this psi naught by p t effective. Okay, so our final equation is then like this: jx. But till now we have only got the current density along the Josephson junction, how it gets modified in the presence of a magnetic field. So if we apply a voltage from here and also measure, then we have derived the equation how much the current density that changes in the presence of a magnetic field. But we have not still derived how much the current changes. And to derive that, we have to integrate this equation over the surface S. Okay. So let's again draw this geometry. So let's try to draw the Josephson junction again. Okay. So let's say our Josephson junction like this, where this region is the normal metal region. Normal metal. This is superconducting region 1 and this is superconducting region 2. So to find out the, and let's say the width of this Josephson junction in this direction is given by L, and this width is given by W. So the length is given by L and the width is given by W, and the width of this normal metal region, that is already we have said that this is T effective, represented by T effective, and this length scale, let's say this length, this is up. So our x-axis is like this along this direction. So x-axis is along this direction. Our x-axis is along this direction. So the small amount of length along this direction, so basically this thing is given by, let's say, dx. So this is our geometry. Now we have to integrate the current density to get the final equation of current. Okay. So now we represent this jx that we have derived in terms of its sine function. Okay, now I have to derive this, integrate this actually. So ds basically, the ds is basically the small area along this region. Okay, so the small area along this region, so this is our width w and this is our width dx. Okay, so the small area we draw a small area, so the current is let's say flowing in this. So the small area, if we consider the small area element ds to be this, so this is ds. So because this is w and this is our dx, so ds is given by w dx. So the small area element is given by this thing, and let's put that there. This gives us this is 0 times w times, now we have to integrate this. So if we choose our origin to be here 0, so as this total length is L, this is L by 2, or this region is minus L by 2. So our integration will be like this, from minus L by 2 to plus L by 2. So our x basically varies from minus L by 2 to plus L by 2. So that's why we have written this 2 pi x delta j dx. Now we have to integrate this equation. Okay. So to integrate this, it will be beneficial to actually write this sine term as a real part of the exponential I term. Okay. So as we know already that sine x can be written as so the sine x can be written as the real part of e to the power ix, or minus ix actually. Okay. So the sine term can be written as e to the power minus ix. Okay. And I multiplied. If we try to see how this happens, so we write e to the power ix. So let's expand this, cos x minus I sin x. Okay, and this I and this I, so cos x plus sin x. Okay, so the real part of this term is sin x. So that's why we can write this sin x as the real part of I e to the power minus ix. Now we also try to write this sign of this function as a real part of some exponential function. Okay, so the interior part just replaces this x, so this will be given as, let's go to the next page. So this will be given as I will be given as jc0 to real part of p. Okay. So this term to delta x. Okay, now let's calculate it explicitly. So if we do the integration over this term, what do we get? So we get real part of I term goes out here, this item, and exponential minus I 2 pi x by lambda j plus delta dot minus I into 2 pi by lambda j minus L by 2 plus L by 2. Okay, so this is our total final integration after integration. Now what do we do here is, basically to simplify it more, we multiply L here. L is the length of the superconjugation junction. Then this gives this real part of I is equal minus I pi a by delta j lambda j. Okay, so this term, now we have to also have taken this term, because this is a constant, so we have taken this term outside. Now the remainder we will only keep these two terms here, so minus 2i right to 2i here, and the other terms we take it outside. And remember, we have multiplied an extra l here, so we have to also divide by this. So this is basically given as pi l by lambda j. Now what is basically the value of pi l by lambda j? Pi l by lambda j is l is, so the lambda j is given by I naught by b. So we have already derived it before, so we will multiply this. So this gives us this, and remember this is the total flux to this normal metal region. So the total flux is noted by 5, so you can write this as 5 by 5. Okay, so finally the I takes the form like this. C naught real part of I into sine of alpha by phi naught by pi 5 by 5 naught. Real part of this times the e to the power minus I delta naught term was outside, you remember, so we break it in this term. So now we have to take the real part of this total term. Okay, so if we take the real part of this total term, we will get as this. Or this can be written as sine of delta naught, where the critical current in the presence of the magnetic field ICB is denoted as this IC in the absence of magnetic field times this equation sine phi 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 naught phi 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 naught. And phi is what? Phi is the what? Phi is the magnetic flux to this normal metal. Phi naught is flux quantum, that is given by h equal to 2. So this is basically how this is our final equation. So we have got that the current in the presence of the magnetic field is changed like this. Okay, so the critical current is changed like this. So this is our final. So this is our final answer. The current in the presence of the magnetic field is changed like this, where the critical current is modified in the presence of the magnetic field like this. So the critical current is modified by this. So this thing gets multiplied to the critical current when we apply an external magnetic field. Now let's take a break for 2 minutes and I'll be back after 2 minutes. Meanwhile, if you have Okay, so let's resume our discussion session now. And the final thing that we will try to do is uh, what do you call it? Okay, so let's hit this thing first. Okay, so let's start our question number 5. Let's start our discussion of question number 5 that says basically how the working principle of the squid basically. So we have talked about the discussion lesson for a lot of time, for a lot of time, and so now we'll see how this reception junction can be used to make a squid device, which is very much useful in the field of experimental condensate physics. So let's start with the so the squid is basically consists of two reception junctions that are connected like this. So this is reception junction 1 and this is reception junction 2. Okay, so this is reception junction 2. And this all, so this is basically the normal metal region and all these things are superconductors. Okay, so this is superconductor 1, this is superconductor 2, and they're connected to this normal metal 1 and normal metal 2. Okay, so this thing is called a squid, which is the full form of, which is the abbreviation of this superconducting quantum interference device. So squid. Now what we do is that we'll see that how the squid basically works. What is the working principle of it? So let's say we have applied a magnetic field whose direction is represented by this conventional notations. Okay, so this is basically outer inside the paper. Okay, so this is basically in the plane perpendicular to the plane of the squid. Okay, so this is basically perpendicular to the plane of the paper. So as you can see. Okay, now what happens is, let's say the current to this Josephson junction 1 that is given by I1 is given by this. and the current in the Josephson junction 2 is given by this. Where delta 1 and delta is called phase, okay, and they are different from each other. So current on I1 is flowing here, then the current I2 is flowing here. Now when they gets superimposed to each other, they try to interfere with each other, okay. So now the total current is then given by I1 plus I2 is equal to ICP sine of delta 1 plus ICP sine of delta 2. So this generates an interference, and so the interference from these things. Now from the Riemann-Lambda theory, we will again use that equation from the Chinshaw-Lambda theory, which gives us that gradient of phi or delta, whatever you say, the phase basically, gradient of phase is pi by v dot d. So we choose a path in such a way that the current density J is 0 for the entire path. So we choose our path is basically like this. So this is our junction. So this one also is a function. So our path is like this. So because this width of this thing normal region is very small, so we can consider that the whole path is through a superconductor where the current density is basically 0. That's why the J is 0. You can say approximately over the entire region. So then this term can be written as delta 1 minus delta 2 because we are going through this region, entire region. So it is here it is delta 1, here it is delta 2. So this term gives us delta 1 by delta 2 into 2 pi by phi naught into phi, where phi is the flux is flowing through this region. Okay, so this is basically the magnetic flux that is flowing through this coil. Okay, so if the radius of this coil is r, this is r, this phi is given as b into y r square. Okay. Okay, so this is the thing, and now what we'll do is that okay, so now we'll put this thing in this equation and see how this I equals. Okay, so I total or IT, this evolves like this. Okay, so 2 equals like this, 2 ICB sine delta 1 plus delta 2 by 2 cos delta 1 minus delta 2 by 2. We have derived that delta 1 minus delta 2 is 2 pi by phi naught times phi. We also know from our previous calculation that in the presence of a magnetic field, this critical current of the Josephson transmission, it gets modified like this. This is naught to sine phi naught, phi prime by phi naught, phi by phi prime by phi naught, where phi prime is magnetic flux flux through the Josephson junctions only, not to the squid. Remember, this only through the Josephson junction. And this phi is flux through the squid loop. So that means if we draw the squid again, so if this is the normal metal region, the magnetic flux that passes only through this region, this normal metal region, that is given by phi prime, and then the magnetic flux that passes through this squid loop means this region. This is given by phi. Okay. So you have to keep this thing in mind, because this is very important. So now let's substitute all this thing in this equation. So this then finally gives us IC 0 sine pi phi naught phi prime by phi naught phi prime by phi naught. Okay. This term is here. Now here we put in the place of phi 1 minus phi 2, we put this thing. So this gives us phi by phi naught times sine delta, but delta till is given by delta 1 by delta 2 by 2. So from here we can see that although, because these places are very thin, so although this phi prime and this phi prime is very small, so this critical current that thing that does not get modified too much. Okay, so if you had used only Josephson junction, so this place is very thin, and that is why this phi prime is very thin. So in the presence of a magnetic field, this total current that does not get modified too much. But when we use it as a squid loop, we can see here that the phi, that is the flux to the squid loop, that is compared very high compared to this phi prime. So that is why this term that is now significant. Okay, so that is why although in the presence of magnetic field, the Josephson junction through the current through the Josephson junction, they are not too much get modulated, but the interferent current, total current, this squid loop, they gets modified due to this term, and because this phi has a significant value. So that is how, in comparison to a Josephson junction, this squid loop, they get much more important, and they are much more sensitive when we try to do any measurement. Okay. So if we see the use of a squid loop, so this device is basically used while we try to detect the magnetic field of a magnetic object, or the magnetization of a magnetic sample. Okay. So because this squid loop is very sensitive, and it basically can detect a magnetic field that is of the order of 10 to the power minus 8 gauss. Okay, so this squid loop can detect this one very small amount of magnetic field, and that is why the squid loop is much more sensitive instrument than any other sensitive instrument that can be used to measure the magnetization of a sample or any magnetic measurement. So the squid loop is much more important setup in the field of experimental quantum physics, but it's much more sensitive than most of the other instruments that we use to measure the magnetization of the sample. Okay. And you can see that this 10 to the power 8 gauss means in the Tesla unit, it is almost 10 to the power minus 12 Tesla. Okay. So you can see this is very small magnetic field that the squid devices can measure, and that is why this squid is called a very sensitive device, and it is used widely through all over the world to use the magnetic field or do any magnetic measurement in the field of experimental quantum. So my discussion on this field, on this Josephson junction and this squid, is over, and so I will end this discussion on this Josephson junction and squid now. And if you have any question, about all these discussions that I made today, you can ask me now. Okay. Okay. Till then, I'll try to save this. Okay, I think it's saved now. Okay, so let's close the presentation here and so there is more. Okay, so that's the end of our discussion session of week number 4. Okay, so let's close this session.